How is your life?
Okay, okay. So thank you very much, Neeraj. So today we will take up the topic of again the air standard cycle in the our last presentation. Means yesterday only we have started with the air standard cycle, and we have discussed the part of the air cycle. So today we will proceed with the same topic, and we will start the now the diesel cycle. So let me share my screen. So this is what we have started yesterday with the air standard cycle. We have studied the basically for the IC engine application, three thermodynamic analysis of the IC engine, then the four-stroke engine and how the cycles are being there. Then also we have studied the basics in the that is the Charles law, then the Lussac law, this is also we have studied, and also the ideal gas law, that is PV is equal to RT. Then polytropic process, that is PV to the power of N is equal to C. This we have studied. Isentropic processes, PV to the power of gamma is equal to C. Okay, so using these equations for the ideal gas, that is PV is equal to MRP. Then isentropic work, how to calculate the isentropic work. So equation which we have discussed yesterday, that is W is equal to MR in bracket T2 minus T1 divided by 1 minus gamma. Then the values of the specific heat constants Cp, Cv, K, and the R, that is a universal gas constant 0.287 kilojoule per kg Kelvin. Properties of the air also we have studied, and the values. And then we have started with the portion of the Otto cycle, and we have studied the Otto cycle, which is being consisting of the two isentropic processes like isentropic compression, isentropic expansion, and also the heat addition and the heat rejection at the constant volume process. So 2 to 3 is nothing but the heat addition constant volume process. Okay, and here the 4 to 1 is nothing but the heat rejection, which is also happening at the constant volume process. Then the various strokes in the this process of the Otto cycle, that is intake stroke, compression stroke, then combustion process, then the power stroke, okay, exhaust blow down and exhaust stroke. So this is what the part which we have studied. Then the thermodynamic analysis of the air standard cycle. Then for isentropic compression, we have studied and we have calculated this equation. Then for a constant volume heat addition, the combustion process, which is being going on when all the valves are closed, all means inlet and exhaust valve of the engine is being closed. Then the process 3 to 4, that is isentropic power or expansion stroke, when the valve is closed, all the valves are closed. Exhaust valve open and intake valve close during the heat rejection, that is exhaust blow down. Then constant pressure exhaust stroke at PO. And then we have determined the equation, derived the equation for the thermal efficiency of the Otto cycle, which is given by NT Otto, that the thermal efficiency of Otto cycle is equal to 1 minus T4 minus T1 divided by T3 minus T2. So thermal efficiency of the Otto cycle, derived this equation we have studied, and the final equation is nothing but efficiency of the Otto cycle is equal to 1 by RC, 1 minus 1 by RC. RC is nothing but the ratio of compression or the compression ratio to the power of gamma minus 1 or K minus 1. So characteristics of the Otto cycle also, the spark ignition engine, then the how, what are the factors basically which are affecting the Otto cycle. That is, if you say, okay, increasing the 1 to 2 again, this will have up 2 to 3, it is a 2 to 3 dash. Again there will be a helpful for a mean effective pressure MEP also we have discussed. and its characteristics of the thermal efficiency with the MEP, relationship between the MEP and P3. This is what we have discussed, and the closing thoughts also with this basically the auto cycle and the PV diagram of the SI engine we have studied, and we know that in the reciprocating engine the clearance volume it is bit left, so therefore the your start PV diagram will start from this point only, and this is the clearance volume, and this is the displacement of the piston. So this part, okay, we have discussed in the yesterday's session, starting with the air standard cycle, and the part of the auto cycle is being covered by me yesterday. Now I am going to move further with the basically the diesel cycle, because we have studied in the contents that we will take up the auto cycle, then we will cover up the diesel cycle, then we will go to the dual fuel cycle. So let me continue with my presentation. So diesel cycle. So in diesel cycle, the fuel is injected into the combustion chamber very late in the compression stroke, which means that in case of the spark ignition engine, the air plus fuel mixture is being sucked inside the cylinder, and same is being compressed. That charge is being compressed, and the spark is produced during the expansion stroke or the ignition of the fuel air mixture. In this case of the diesel engine, the fuel is injected into the combustion chamber very late at the end of the compression stroke, which means that in the beginning stroke or in the suction stroke, only air is being sucked inside the cylinder, and the air is being compressed to such an level when the atomized diesel is being sprayed, then the combustion process is start. So this is the difference between the auto cycle and the diesel cycle. Here fuel used, as the name is diesel cycle, the fuel used is nothing but a diesel engine and the diesel, and in earlier case the spark ignition engine, the fuel used is nothing but the petrol. Due to ignition delay and the finite time required to inject the fuel, combustion lasted into the expansion stroke. So this keep the pressure at peak levels well past the TDC, and combustion process is approximated as the constant pressure heat input in an air standard cycle. So this is the indicator diagram of an CI engine. Look at the indicator diagram. You can see that the pressure and the volume diagram, PV diagram. Again, you can see the various processes, suction and the exhaust. What is the difference which you can significantly see here? In case of the SI engine, the constant volume heat addition is there. Okay, and in case of the basically the diesel engine, which you can see for here, the constant pressure heat addition is there. So this is the main difference. This is the actual indicator diagram which is shown to you, which is available in front of your screen. But if you compare it with the CI engine and the SI engine, this will be the one of the prominent difference which you can see from the indicator diagram. Now, diesel air standard cycle. So again, the in the reciprocating engine, the clearance volume will be there. So you can see that some space is left here in the pressure volume diagram as well as the temperature entropy diagram. Now, in case of the pressure volume diagram, the process 6 to 5 or process here 0 or 6 to 1 is basically the suction process. Now, in this suction process, only the air is being sucked inside the cylinder. In case of the compression ignition engine, try to look at my statement. In case of the CI engine, the fresh charge like a air plus petrol, air plus fuel mixture is being sucked inside the cylinder. Now, in case of the diesel engine, only air is sucked, means air is provided in the suction stroke into the cylinder of the engine, and then Here the 1 to 2 is nothing but the compression of the gas, compression of the air which is sucked inside the cylinder, and 2 to 3 is the heat addition. What was the heat addition which was taking place in case of the spark ignition engine, in case of the petrol engine? In case of the petrol engine, the constant volume heat addition was there. What is the change here? In case of the diesel engine, the constant pressure heat addition is there. So this 0.223 is nothing but a heat addition. Due to the heat addition, the burning of the gases, expansion of the gases is being taking place, and we get an expansion stroke, or which is called as also the power stroke. So again, the adiabatic expansion is there, like a 3 to 4. Adiabatic compression is there, 1 to 2. Adiabatic expansion is there, that is 3 to 4, which is also called as the isentropic process. And 4 to 1 is nothing but the exhaust blowdown or the exhaust stroke, wherein all combustible gases which are present inside the cylinder, that gases is being removed and exhausted to the atmosphere through the exhaust pipe or through the silencer which we called as the tailpipe of the engine. So therefore this 4 to 1 and 1 to 6, this is what the exhaust process is there. So this constant volume heat rejection or exhaust removal is there from 4 to 1. Then look at the temperature entropy diagram. Okay, 1 to 2 is nothing but the isentropic compression. So entropy remains constant. So 1 to 2, you can see that entropy at point 2 is equal to the entropy at point 1. Then 2 to 3 is nothing but the constant pressure process, heat addition at constant pressure process. So 2 to 3, here you can see that temperature T3 minus temperature T2 is the heat added to the compressed air or the compressed gas. Then 3 to 4 is nothing but again isentropic expansion. Isentropic expansion means again the entropy remains constant. So entropy at point 3 is equal to the entropy at point 4, and T3 is greater than T4. The temperature will reduce down in the expansion stroke. Then from the 4 to 1 is nothing but the removal of the exhaust gases or the exhaust stroke, which is again the 4 to 1. 4 to 1 is a expansion. 2 to 3 is nothing but the basically the compression, here heat addition. Then 3 to 4, it is isentropic expansion. And 4 to 1, the exhaust removal process which is being going on in the diesel cycle. So by looking at the air standard cycle, you can easily identify the differences in the auto cycle and diesel cycle, and the major changes which are being there in the construction of the engine cylinder and the engine. Now thermodynamic analysis of the air standard cycle. The process 61 is nothing but the constant pressure intake of air at PO. PO means atmospheric pressure, क्योंकि ओके सक्शन जो होता है कंप्रेशन इग्निशन इंजन में, मतलब डीजल इंजन में हम लोग एयर सक करते हैं विच इज अवेलेबल एट द एटमॉस्फेरिक प्रेशर, and inside the cylinder that air is compressed, okay, with respect to the compression ratio of the cylinder. और उसके बाद में okay, the fuel is sprayed, atomized fuel is sprayed, whereas the burning will takes place. So process 61 is the constant pressure intake of the air at PO, intake valve open and the exhaust valve closed. So P1 is equal to P6 is equal to P0. So W work done 6 to 1 is PO in bracket the V1 minus V6. Then process 1 to 2, that is isentropic compression stroke. So isentropic compression stroke, here all the valves are in the closed condition. So T2 is equal to T1 in bracket V1 by V2 to the power of gamma minus 1. So is equal to T1 in bracket V1 by V2 to the power of gamma minus 1. So T1 in bracket RC to the power of gamma minus 1. P2 is equal to P1 in bracket V1 by V2 to the power of gamma at P1 is in bracket V1 by V2 to the power of gamma P1 RC to the power of gamma. So Q1 to 2 word is nothing but the zero. It is the isentropic compression uh, stroke. So here the work done from 1 to 2 in process 1 to 2 is equal to P2 V2 minus P1 V1 divided by 1 minus K, or R in bracket T2 minus T1 divided by 1 minus K. Okay, so it is W12 is being given by U1 minus U2 is equal to CV, okay, in bracket T1 minus T2. Then constant pressure heat input combustion, that is all valves are closed. So Q2 to 3 is equal to Q in is equal to MF QHV CV into is equal to MMCP in bracket T3 minus T2 is equal to MA plus MF into CP in bracket T3 minus T2. So QHV into NC is equal to AF plus 1 in bracket CP in bracket T3 minus T2. So Q23 is equal to Q in I in heat input CP is equal to in bracket T3 minus T2 is equal to H3 minus H2. So work done 2 to 3 is equal to Q23 is equal to U3 minus U2 is equal to P2 in bracket V3 minus V2. So T3 is equal to T max. Then cutoff ratio. So cutoff ratio is beta. The what is the cutoff ratio? The change in volume that occurs during combustion given as ratio is called as the cutoff ratio. So from ideal gas equation, P2 V2 divided by T2 is equal to P3 V3 divided by T3. So therefore T3 by T2 is nothing but the V3 by V2, because rearranging the terms, and for this ideal gas equation the P3 is equal to P2. So when P3 is equal to P2, that is T3 divided by T2, we have taken a temperature ratio is equal to V3 divided by V2. So therefore, the cutoff ratio beta is nothing but V3 divided by V2 is equal to mu3 divided by mu2 is equal to T3 divided by the T2. This is called as the cutoff ratio of a CI engine. Then isentropic power, or the isentropic expansion stroke. Here in this situation also, both the valves of a CI engine, they are into the closed condition. So therefore Q3 to 4 is equal to 0, and then T4 is equal to T3 in bracket V3 by V4 to the power of gamma minus 1, okay, is equal to, hello, हेलो, नहीं कौन बोलता है? मकरंद कुठून बोलताय? नाही नाही नाही, पुण्यात ना, मकरंद कुठल्या कॉलेजला? हो तरी पण मी विचारत आहो की कुठे आहेत तुम्ही समजा. हो पुण्यात म्हणजे कुठल्या फील्डला आहे तुम्ही? कोणत्या कोणत्या कंपनीत एचआर आहात तुम्ही? अच्छा, आर आर इंडस्ट्रियल प्रायव्हेट पॅकेजिंग लिमिटेड. हां, बरं 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 बरं. बरं, ठीक आहे ठीक आहे. So T4 is equal to T3 in bracket V3 by V4 to the power of gamma minus 1, or T3 is in bracket V3 by V4 to the power of gamma minus 1. So therefore P4 is equal to P3 in bracket V3 by V4 to the power of gamma, or P3 in bracket V3 by V4 to the power of gamma. So work done in the power stroke 3 to 4 is nothing but P4 V4 minus P3 V3 divided by 1 minus gamma. Again, okay, it is P3 taken outside and common. Therefore, the isentropic power or the expansion stroke, if you look at the as this process, the 3 to 4, how it is being taking place in this process 3 to 4. Okay, that is the power stroke. Here the 3 to 4 process. Okay, this is your 3 to 4 process. So 3 to 4 process, that is P3 P4 V4 minus P3 V3 divided by 1 minus gamma is equal to R in bracket T4 minus T3 divided by 1 minus gamma is equal to U3 minus U4 is equal to CV into T3 minus T4. So this is the equation for the power stroke W in the power expansion stroke, that is CV is equal to T3 minus T4. Similarly, analyzing the constant volume heat rejection, that is exhaust blowdown process. So exhaust valve open and intake valve close, that is V pi is equal to V4 is equal to V1 is equal to VBDC. So work done from 4 to 5 is equal to 0. So Q4 to 5 is equal to Q out is equal to MMCV in bracket T5 minus T4 is equal to MMCV in bracket T1 minus T4. So Q4 to 5 is equal to Q out is equal to CV in bracket T5 minus T4 is equal to U5 minus U4 is equal to CV into T1 minus T4. So exhaust valve open and the intake valve closed. Then constant pressure exhaust stroke at PO. So exhaust valve opens and the intake valve close. That is P5 is equal to P6 is equal to PO. So work done 5 to 6 is PO in bracket V6 minus V5 is equal to PO in bracket V6 minus V1. Then thermal efficiency of the Otto cycle. Thermal efficiency of the Otto cycle, that is Otto cycle thermal efficiency is equal to W net divided by Q in, work done divided by heat provided, 1 minus Q out divided by Q in. So 1 minus CV in bracket T4 minus T1 divided by Cp in bracket T3 minus T2. So therefore CV by Cp is gamma. So therefore 1 minus T4 minus T1 into divided by gamma in bracket T3 minus T2. So 1 minus T1 in bracket T4 by T1 minus 1 divided by T2K into T3 by T2 minus 1. For combined gas law, P2V2 divided by T2 is equal to P3V3 divided by T3. So therefore T3 by T2 is equal to V3 by V2 is equal to beta, and T3 is equal to T2 beta. That is the combined gas law. Beta is where we have taken the cutoff ratio. Then for isentropic compression, this was the thermal efficiency of a diesel cycle. For isentropic compression, T2 is equal to T1 into RC to the power of gamma minus 1. So substituting the isentropic expression into the expression obtained from combined law, we arrive at an equation, that is T3 is equal to T1 in bracket gamma RC to the power of gamma minus 1 into beta. And from the isentropic expansion equation, that is T4 by T3 is equal to V3 by V4 to the power of gamma minus 1. So therefore T4 is equal to T3 in bracket V3 by V2 and V2 by V4 to the power of gamma minus 1. Therefore T4 is equal to T3 into in bracket beta 1 by RC to the power of gamma minus 1, and then rearranging this term, T4 is equal to T1 in bracket RC to the power of gamma minus 1 beta multiplied by beta 1 by RC to the power of gamma minus 1. So therefore, T4 is equal to T1 into beta to the power of gamma minus 1 cutoff ratio. So with rearrangement, this thermal efficiency of a diesel cycle can be written as thermal efficiency of the diesel cycle is equal to 1 minus 1 by RC to the power of gamma minus 1 in bracket BK to the power of minus 1 beta minus 1 beta to the power of gamma minus 1 divided by gamma in bracket beta minus 1. So where RC is the compression ratio and gamma is Cp by Cv and beta is the cutoff ratio. Note the term in the square bracket is always larger than the unity. Okay, so for the same compression ratio RC, the diesel engine has a lower thermal efficiency than the Otto cycle. Try to understand this term because the term in the square bracket, what is the term in the square bracket? Beta to the power of gamma minus 1 divided by gamma in bracket beta minus 1. So this term in the square bracket is always larger than the unity. So for the same compression ratio, the has diesel has a lower thermal efficiency than the Otto cycle. So therefore, the compression ignition engine higher compression ratios are there compared to the SI engine to ignite the fuel, which means that the difference is there. Here you can find out the difference. In case of the petrol engine, the air fuel mixture is being taken inside the cylinder during the suction stroke, and then it is ignited with the help of the spark ignition system, or with the help of the spark plug which is producing the spark, and then the burning of the air fuel mixture start. In case of the compression ignition engine, only air is being sucked inside the suction stroke, and air is compressed to such a level, we have to compress it to the such a level that at the end of the compression, when the fuel means the diesel is sprayed, atomized fuel is being sprayed into the cylinder, the burning of fuel should start. So therefore, the compression engine, it requires higher compression ratio compared with the spark engine to ignite the fuel. So thermal efficiency of a diesel cycle, that is cutoff ratio, is not a natural choice of independent variable. More suitable parameter is the heat input, and the two are related by beta is equal to 1 minus gamma minus 1 divided by gamma in bracket q in divided by p1 v1, okay, is equal to 1 by RC to the power of gamma minus 1. So substituting the cutoff ratio equation in the thermal efficiency equation for diesel cycle, it is possible to plot the same curves. Okay. So these are the thermal efficiency diesel life cycle curves. So let me check whether it is going on perfectly or not. Okay. ठीक है. So we will have a 1 minute break and we will continue again. So let me continue with the point where I left the discussion for the biological break. So thermal efficiency characteristics of a diesel cycle. The higher efficiency is obtained by adding less heat per cycle, that is queuing. You can see the even the comparison also. This is the that is indirect uh, here the efficiency and the compression ratio. This is compression ratio versus the indicated mean effective pressure. This is indicated efficiency. This is indicated mean effective pressure. And you can see here the comparison of the Otto cycle and the diesel cycle. So in diesel engine, the fuel cutoff ratio depends on the output maximum for the maximum output. Then let us consider the next cycle in the air standard cycle, the dual fuel cycle. So in the dual fuel, the fuel is injected earlier in the compression stroke. So 20 degree before the TDC, that is top dead center. Some of the combustion occurs almost at constant volume at TDC, similar to the Otto cycle. The fuel is being injected at TDC, and the combustion of this fuel keeps the pressure high into the expansion stroke. The heat input process of combustion is approximated by dual process of constant volume followed by the constant pressure. So this will be the change in the indicator diagram of a dual fuel cycle. So in the indicator diagram of the dual fuel cycle, you can see that here also the heat addition is at the constant volume. So heat addition is at the constant volume and at the constant pressure in case of the dual fuel cycle. So here look at the pressure and volume diagram of an dual fuel engine. The this portion is being shown as a left for the clearance volume. Okay, this is the PV diagram, that is 6 to 1 is nothing but the your suction stroke. Then 1 to 2 is the isentropic expansion. Sorry, isentropic, basically the compression. 2 to x and 2 to 3 x to 3. So this is the dual fuel cycle. This is change. Dual fuel means in case of the Otto cycle, the constant volume heat addition is there. In case of the diesel cycle, the constant pressure heat addition is there. Now, in case of the dual fuel cycle, the heat addition is being taking place both at the constant volume and at the constant pressure, which means that 2 to x and x to 3, which shows that 2 to 3 is nothing but the heat addition, and 3 to 4 is the expansion stroke, wherein again the adiabatic expansion is being taking place, and 4 to 1 is nothing but the exhaust stroke. Look at the temperature entropy diagram here. 1 to 2 compression, 2 to x and x to 3 is the temperature increase, means the heat addition. Okay, one heat addition is at the constant volume, another heat addition is at the constant pressure. Then 3 to 4 is the expansion, adiabatic expansion, wherein again the entropy remains constant, and 4 to 1 is the exhaust stroke, where the combustible gases are removed from the exhaust from the cylinder of the engine through exhaust pipe. Then it is exhausted, it is circulated to the atmosphere. Then thermodynamic analysis of a air standard dual cycle. The analysis of air standard dual cycle is same as that of the diesel cycle, except the for the heat input process, that is combustion is taking place in the 2x and 3. So process 2x, that is constant volume heat input, first part of the combustion, all valves are closed. So Vx is equal to V2 is equal to Vtdc. So W2 minus X is equal to 0. So Q2 minus X is equal to mm Cv in bracket Tx minus T2 is equal to Ma plus Mf Cv in bracket Tx minus T2. So Q2x is equal to Cv in bracket Tx minus T2 is equal to Ux minus U2. So therefore Px is equal to Pmax is equal to P2 in bracket Tx divided by the T2. So pressure ratio is defined as the rise in pressure during combustion, okay, given as the ratio. So here alpha is equal to Px by P2 is equal to P3 by P2 is equal to Tx by T2 is equal to alpha is equal to pressure ratio is equal to the 1 by Rc to the power of gamma in bracket P3 by P1. So Rc is nothing but the ratio of compression. Therefore, P2 by P1 is equal to V1 by V2 to the power of gamma is equal to Rc to the power of gamma. So, P2 by P1 is equal to Rc to the power of gamma. Process X3 constant pressure heat input, that is second part of the combustion. Here also all valves are closed. So P3 is equal to Px is equal to Pmax. So W2 to X is 0. So Qx3 is equal to mmCp in bracket T3 minus Tx is equal to Ma plus Mf in Cp in bracket T3 minus Tx. So Qx to 3 x dash 3 is equal to Cp in bracket T3 minus Tx is equal to H3 minus Hx. So Wx3 is equal to Qx3 minus Q3 minus Qx is equal to Px in bracket V3 minus Vx is equal to P3 in bracket V3 minus Vx. So T3 is equal to Tmax. So thermal efficiency of a dual cycle. So thermal efficiency of a dual cycle, that is dual cycle is equal NT dual is equal to W net divided by Q in is equal to 1 minus Q out divided by Q in. So 1 minus in bracket CV in bracket T3 T4 minus T1 divided by CV in bracket Tx minus T2 plus Cp in bracket T3 minus Tx. Therefore, the thermal efficiency of a dual cycle is equal to 1 minus T4 minus T1 divided by Tx minus T2 plus K in bracket T3 minus Tx. So this equation can be rearranged to get the further equation as a efficiency of a thermal efficiency of a dual cycle is equal to 1 minus 1 by Rc to the power of gamma minus 1 in square bracket alpha beta to the power of gamma minus 1 divided by gamma alpha in bracket beta minus 1 plus alpha minus 1. So let us see the comparison of Otto cycle, diesel cycle and the dual cycle. So comparison of the Otto cycle, diesel cycle and the dual cycle for the same inlet conditions and the same compression ratios and same heat removal, the efficiency of Otto cycle is greater than the efficiency of dual cycle, and efficiency of the dual cycle is greater than the efficiency of the diesel cycle for the same inlet condition, for the same compression ratio and same heat removal. Try to see that efficiency of Otto cycle will be greater than that of the efficiency of the fuel cycle, and efficiency of the dual cycle is greater than the diesel cycle. So on a diagram of PV diagram, these cycles are being plotted. That is 1 to 2. Okay, 1 to 2 is nothing but the basically the compression. Then 2 to 3, if you go to the 2 to 3, naturally it is a auto cycle. Then 3 to 4, okay, and 4 to 1. So this is auto cycle. Diesel cycle, what is diesel cycle? 1 to 2, okay, and then 2 to 3, that is constant pressure heat addition in diesel cycle, then 3 to 4, and then 1. Okay, and here in this case, dual fuel cycle, if you see the dual fuel cycle, 1 to 2, okay, this is 1 to 2 compression, then 2 to 3, that is constant volume heat addition, and then 2 to x and x to 3b, x to 3b constant volume, 2 to x constant volume, and 2 to x is nothing but the constant pressure. So x to 3b is a constant pressure heat addition. So cycle will be 1 to 2, 2 to x, x to 3b, and 3b to the 4 is nothing but the cycle in the dual fuel. Same is the case here, the temperature entropy diagram. Here 1 to 2, okay, 1 to 2 is there. Then 2 to 3c is for the auto cycle. 2 to 3 is for auto cycle. Then 2 to x and x to 3b, 3b to 4 is for the dual fuel cycle. And here the 2 to 3a, 2 to 3a, that is the auto cycle, and the 2 to 3a. And what is diesel cycle? 2 to 3c. 2 to 3c is nothing but the diesel cycle. So therefore here the heat addition in the auto cycle, that is 2 to 3a, you can see here the more. In diesel cycle it is less, and in case of the dual fuel cycle, it is more than in between the diesel and auto cycle, but it is carried out in the two stages. That is, one is nothing but the constant volume, and another is nothing but the constant pressure heat addition. So these are the differences in the auto cycle, dual fuel cycle, and the diesel cycle. Look at these differences. That is, auto is nothing but 1 2 1 2 3 4 1. Dual is 1 2, okay, 1 2 x 3b, and then 4 1. Diesel is 1 2 3c 4 1. Same is the case here, 1 2 3a, 1 2 3a auto cycle 4 1. Dual fuel cycle, that is 1 2 3 x 3b 4.1, and diesel cycle 1 2, then 3c, okay, 4 3c 4 1. Then for the same inlet conditions, we have studied this. For the same inlet condition, the same prick ratio, same heat removal, the efficiency of the diesel cycle is greater than the dual fuel than the auto cycle. So earlier we have seen that for the same inlet condition, the same compression ratio, same heat addition. Now the second case we are seeing. Hello, हा संदेश. Good evening. बरोबर, दोन फाईल झालेल्या आहे का? ठीक, ठीक आहे. हो हो, बाकीच्या पण तशाच करून टाकायचे समजा, है ना. हो 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 हो. ठीक आहे, मला थोडा वेळ लागेल पण चेक करायला. तुम्ही चालू करून द्या ना, चालू ठेवून द्या ना, उद्यापर्यंत आपण करून टाकू. हा. हम्म. So for same inlet condition, the same compression ratio, the same heat addition, the efficiency of Otto cycle is greater than dual cycle, and efficiency of dual cycle is greater than the diesel cycle. So for the same inlet condition and same peak pressure and same heat removal, in case of diesel engine, the thermal efficiency is greater than the dual cycle and then the Otto cycle. So there are three, four conditions which you are seeing here. What is the first condition? Let me see here. ते पेज नंबर नाही टाकलाय ना त्याच्यात. पीडीएफ कोण सांगितलं वर्ड मध्ये कन्वर्ट करायचं आहे? स्कॅन कुठं वर्ड मध्ये कन्वर्ट होते का? कोण? अरे स्कॅन पेजेस नाही होते यार वर्ड मध्ये कन्वर्ट. तू काही नको सांगू. पेज नंबर टाकायचे आहे ना त्याच्यावर. आपल्या याच्यावर स्कॅनिंगच्या आधी पेज नंबर टाकायचे आहे. हॅलो. So the we were on the topic of basically the comparison of the auto cycle, then the diesel cycle and the dual cycle. So for the same inlet condition, the compression ratios and same heat removal, that is thermal efficiency of the auto cycle is greater than the thermal efficiency of the dual cycle, and the thermal efficiency of the dual cycle is greater than the thermal efficiency of the diesel cycle. So for the same inlet condition and the same compression ratio and same heat removal. Now we will go to the next comparison of the auto cycle, diesel cycle and the dual cycle. For the same inlet condition, the same peak pressure and same heat removal, efficiency of the diesel cycle is greater than the efficiency of the dual cycle and auto cycle. Now here, what the change we are seeing for same inlet condition and same peak pressure and same heat removal. So here you can see here the pressure volume diagram, that is 1 to 2a. So this is 1 to 2a, which is a auto cycle, then 2a to 3 auto cycle, 3 to 4 and 4 to 1. What is dual cycle now? 1 to 2b dual cycle, 2b to x and x to 3 and 3 to 4 and 4 to 1 dual fuel cycle. In diesel cycle, directly from 1 to 2c, then 2c to 3 and 3 to 4 and 4 to 1. So here you can see that the specific volume we have plotted versus the P to V. Here the specific volume, this is between this point number 1 and point number 2a. In case of the dual fuel, the specific volume, that is point number 1 and 2b, it is being increased. And in case of the diesel cycle, that is specific volume 1 to 2c, it is being increased because compression ratio is high in case of the diesel engines. If you look at the temperature entropy diagram, you will find the similar kind of change. For example, the auto cycle is nothing but the 1 to 2a, okay, 2a to 3, 3 to 4 and 4 to 1. What about the dual fuel cycle? 1 to 2b, which means that the heat addition here, temperature difference is there between 2b and 2a. Okay, temperature 2b is higher than that of the 2a. So even though the constant entropy process is there, but 1 to 2b, then 2b to x for a dual fuel cycle, then x to 3 and 3 to 4 and 4 to 1, that is a dual fuel cycle. Now if you look at the diesel engine, the 1 to 2c, where the 2c is the highest temperature here compared with the auto cycle and the dual fuel cycle. So 1 to 2c, then 2c to 3, then 3 to 4 and 4 to 1. So if you look at the pressure volume and the temperature entropy diagram, the specific volume has been increased in case of the diesel engine. Similarly, here the heat addition, that is temperature 2C is greater than that of the 2B and the 2A, which means that the for the same inlet condition, the same peak pressure and same heat removal, the efficiency of the diesel engine is greater than the efficiency of the dual fuel engine, and also it is greater than the efficiency of the auto cycle. Now it is completely rearranged, completely changed compared with the earlier slide. In earlier slide, what we have compared, that the for same compression ratio and same heat removal, auto cycle is having a highest efficiency than the dual cycle and the diesel cycle. And now what we are talking about, the for the same peak pressure and same heat removal, the efficiency of diesel cycle is greater than that of the dual cycle and the auto cycle. Now this is the third comparison. Same inlet condition, the same compression ratio, and the same heat addition. Okay, so look at this one, that is for the same inlet condition, same compression ratios.
हॅलो सर.
Hello.
हां सर, पवार मॅडम बोलताय.
So comparison of the Otto cycle, diesel cycle, and the dual cycle for the same inlet conditions, the compression ratios and the same heat addition, the efficiency of the Otto cycle is greater than the efficiency of the dual cycle and efficiency of the diesel cycle. Again, here what we see here, for the same compression ratio, because in the compression ignition engine the compression ratio has to be high, it cannot be kept same as that of the auto cycle or the petrol engine. So therefore, okay, same compression ratios and same heat condition, the auto cycle is having a greater efficiency than the dual fuel cycle and than the diesel cycle. So look at these processes. So this is your 1 to 2 compression, then 2 to 3 auto cycle, 3 to 4, and 4 to 1. Okay, then dual fuel cycle. Dual fuel cycle is nothing but 1 to 2, 2 to 2 dash, constant volume heat addition, then 2 dash to 3 dash, then 3 dash to 4 and 1. And here the diesel cycle, that is 1 to 2, then 2 to 3 dash, constant pressure heat addition, 3 to 4, and then 4 to 1. Same is on the temperature entropy diagram. If you look at the 1 to 2, okay, then 2 to 3, 3 dash, 3 dash to 4 dash, 4 dash to 1. Like that. 1 to 2, 2 to 2 dash, 2 dash to 3 dash, 3 double dash, 3 double dash to 4 double dash, and then 1. And 1 to 2, 2 to 3, and 3 to 4, and 4 to 1. So efficiency of the Otto cycle is greater than the efficiency of the dual cycle and efficiency of the diesel cycle. So with this, today we have completed the topic of the basically the air standard cycle, that is Otto cycle, then the diesel cycle, and the dual fuel cycle, and the its characteristics comparison. So let me check whether it is going on correctly or not, and we will move ahead with the gate examinations questions. Okay. So gate questions, previous years gate questions. So which one of the following is not a necessary assumption for the air standard auto cycle? Because in gate 2008, was the question, that all processes are both internally as well as externally reversible. In case of the auto cycle, then intake and exhaust processes are constant volume heat reduction processes. Then the combustion process is a constant volume heat addition process, and working fluid is an ideal gas with a constant specific heat. So out of these four sentences which is being given, which is not necessarily a assumption for the air standard cycle, because already it is true, it is not the assumption that intake and exhaust processes are constant volume heat reduction processes. So it is a constant pressure process. Then this an engine working in on air standard auto cycle has a cylinder diameter of 10 centimeter and stroke length of 15 centimeter. The ratio of specific heats of air is 1.4 if the clearance volume is 196.3 cc and the heat supplied per kg of air per cycle is 1800 joule per kg. Then the work output per cycle per kg of air. So this question is being given to you, and four options are being given, that is 879.1 kilojoule, 890.2 kilojoule, 895.3 kilojoule, 973.5 kilojoule. So don't try to just take any value. You should know the fundamentals, how to solve the numerical and the concerned equation. Because if you click on any one, because four options are being given, and if you tick on any one, then in that case you will be losing the marks, and also there will be a negative marking in some section. So unnecessarily you will be losing your marks in the examination. So therefore, how to solve such kind of numerical? If you look at here, this is the pressure volume diagram, and this is the VC, the clearance space which is being provided. Then the process is 1 to 2, 2 to 3, 3 to 4, and 4 to 1. So 1, 2, 3, 4, 1 is the basically the process. Then initial volume V1 is nothing but the pi by 4 d square into L. What is the d is nothing but the diameter of the cylinder, which is given as the 10 centimeter, and L is the length of stroke, which is given in this numerical as a 15 centimeter. So initial volume is being calculated as pi into zero point 0.1 square divided by 4 into 0.15 meter cube. So therefore, the 1.1781 into 10 to the power of minus 3 is the initial volume. What is the final volume? Final volume means at the point 2, that is final volume at the point 2 is equal to 196.3 cc. It is being given as, if the clearance volume is 196.336 cc, so 0.1963 into 10 to the power of minus 3 meter cube, because it is cubic centimeter it is given. So 10 to the power of minus 3 VC. So compression ratio is nothing but V1 plus VC divided by VC. So V1 is nothing but your 1.1781 into 10 to the power minus 3. V1 plus VC is nothing but your this is the 0.1963 into 10 to the power of minus 3 VC divided by VC is equal to 7. So this compression ratio we have calculated as a 7, and then we know the equation to calculate the efficiency of the Otto cycle. That is, efficiency is being given by 1 minus 1 by RC to the power of gamma minus 1 is equal to 1 minus 1 by compression ratio already we have calculated, that is C is equal to 1.7 7 to the power of 1.4 minus 1, and efficiency of the auto cycle is coming out to be 0.40 Now work done we have to calculate. Work output is equal to efficiency into heat input. So what is the efficiency? 0.5408, and the heat input, heat provided, that is Q is nothing but Q is given as where Q is given, yes, Heat supplied per kg of air fuel cycle is 1800 kilojoule per kg Kelvin. So therefore, work done is equal to 973.5 kilojoule. So with this kind of question, you are basically the all the test has been conducted, and here the you must know the formula, you must know the fundamental, you must be able to draw the PV diagram, and then you have to solve the particular numerical which is given in the gate examination. Now coming to the third example, for an engine operating on air standard auto cycle, the clearance volume is 10% of the swept volume. The specific heat ratio of air is 1.4, and the air standard cycle efficiency we have to calculate. So look at this question. So 38.3 options are given, 39.8. Okay. Then 60.2 and the 61.7. So these are the four options which we have given. So therefore, but do not tick again any value. Okay. So compression ratio RC is equal to 11, which is being given. That is for an engine operating on air standard cycle, the clearance volume is 10% of the swept volume. Okay, 10% of the swept volume. So compression ratio is being taken as 11. Then if thermal efficiency is 1 minus 1 by RC to the power of gamma minus 1 is equal to 1 minus 11 to the power of 1.4 minus 1 is equal to 0.615. So 0.615 is the correct answer, which means that 61.5%. So closest option is here 61.5%, that is 61.7%. Then an ideal air standard auto cycle has a compression ratio of 8.5 if the ratio of the specific heats of Y is 1.4, then what is the thermal efficiency in percentage of the auto cycle? So again, the four options are given to you, that is 57.5%, 45.7%, 52.5%, and 95%. So efficiency of the auto cycle is equal to 1 minus 1 by RC to the power of gamma minus 1 into 100% is equal to 1 minus 1 by 8.5 to the power of 1.4 minus 1 into 100 is equal to 57.5%. So this is the fourth question. Yes, third and fourth. And the fifth question, that is in an air standard auto cycle, the compression ratio is 10. The condition of the beginning of the compression process is 100 kilopascal and 270 degree centigrade. Heat added at constant volume is 1500 kilojoule per kg, while 700 kilojoule per kg of heat is rejected during the other constant volume process in the cycle. Specific heat gas constant for the air is equal to 0.287 kilojoule per kg Kelvin. The mean effective pressure in kilopascal of the cycle is mean effective pressure is equal to area of PV diagram divided by length of the PV diagram. So if you look at the PV diagram which we have drawn here, this is regarding the auto cycle, that is 1 to 2, 2 to 3, 3 to 4, and 4 to 1. Here heat supplied is nothing but the 1500 kilojoule per kg, while 700 kilojoule per kg of heat is being rejected during the other constant volume process. This process is also constant volume heat addition. This is constant volume heat rejection. So what we need to calculate the here the mean effective pressure, and what we have to calculate heat added at a constant pressure is also given. So mean effective pressure which you have to calculate in kilopascal. So mean effective pressure is nothing but the area under the PV diagram divided by the length of the PV diagram. So work done divided by delta V. So R is equal to V1 by V2, which is given as compression ratio as a 10. So P1 V1 is equal to RT1. So therefore V1 is equal to 0.27 into 300 divided by 300 is equal to V1 is equal to 0.861 kg per meter cube. So area under the PV diagram, that is Q1 minus Q2 divided by V1 minus V2 is equal to 1500 minus 700 divided by 0.861, which you have calculated, minus the 0.0861. So it coming out to be 10232 kilo Pascal. So V1 value which we have calculated, that is 0.861. P1 V1 is equal to RT1. Then P2 V2 value we have to calculate, that is 0.0861. And then finally answer is coming out to be 1032 kilopascal. So this is the fifth question on the Otto cycle. So let me check whether it is going on perfectly or not. Okay, yes, it is going on perfectly. Let me take a biological break and then we will continue with the some more numericals on this topic. हम्म, चालू हो आणून नंतर हो So the what kind of questions are being asked? Okay. So an engine working on air standard Auto cycle is supplied with an air at zero point 0.1 megapascal and standard Auto cycle is supplied with an air at zero point 0.1 megapascal and standard Auto cycle is supplied with an air at zero point 0.1 megapascal. Are you able to see my screen? Is supplied with an air at 0.1 megapascal. Are you able to see my screen? Yes, yes. So an engine working on air standard Auto cycle is supplied with a air of zero point 0.1 megapascal and 35 degrees centigrade. The compression ratio is 8. The heat supplied is 500 kilojoule per kg. The property data for the air Cp is equal to 1.005 kilojoule per kg Kelvin, Cv is equal to 0.718 kilojoule per kg Kelvin, R is equal to 0.287 kilojoule per kg Kelvin. The maximum temperature in Kelvin of the cycle is correct to the one decimal which you have to calculate. Okay, that is coming out to be 1.02 1402 to 1046. Then this is the frictionless circular piston area of 10 to the power of minus 2 meter square and mass 100 kg sinks into a cylindrical container of the same area filled with water of density 1000 kg per meter cube as shown in the figure. The container has a whole of area 10 to the power of minus 3 meter square at the bottom and that is open to the atmosphere. Assuming there is no leakage from the edges of the piston and considering the water to be incompressible, the magnitude of the piston velocity in meter per second you have to calculate. So now this condition gate 2018 again it is being given. Then vehicle is powered by spark ignition engine follows air standard cycle with gamma is equal to 1.4. The engine generates 70 kilowatt while consuming 10.3 kg per hour of fuel. The calorific value of fuel is 44,000 kilojoule per kg. The compression ratio is correct to the two decimal. ठीक है. So propane C3H8 is burned in an oxygen atmosphere with 10% deficit oxygen with respect to the stoichiometric requirement, assuming no hydrocarbons in the product. The volume percentage of the CO in the product is being given. So here, this type of questions will be there in the here. Okay, see what we have studied. For the same values of peak pressure, peak temperature and heat rejection, the correct order of the efficiencies of the Otto cycle, dual cycle, and diesel cycle. That is, efficiency of the diesel cycle is greater than the dual cycle and the Otto cycle for the same values of the peak pressures, peak temperatures, and the heat rejection. The air standard cycle, diesel cycle, consists of the following process. That is, air is compressed isentropically. Hello.
हाँ कुठे
So the air standard diesel cycle consists of the following processes: 1 to 2, that is air is compressed isentropically; 2 to 3, heat is added at constant pressure; 3 to 4, air expands isentropically to the original value; and 4 to 1 is heat is rejected at a constant volume. So, if the gamma and T denote the specific heat ratio and the temperature respectively, the efficiency of the diesel cycle is being given by 1 minus, okay, 1 minus T4 minus T1 divided by T3 minus T2. 1 to 2, 2 to 3 is given, or 1 minus T4 minus T1 divided by gamma in T3 minus T2, or 1 minus gamma in bracket T4 minus T1 divided by T3 minus T2, or 1 minus T4 minus T1 divided by gamma minus 1 into, okay, T3 minus T2. So what is your correct answer? That is 1 minus T4 minus T1 divided by gamma into T3 minus T2. So most of the numericals will be there, which you have to understand. That is, a diesel engine has a compression ratio of 17, and cutoff ratio takes place at 10% of the stroke, assuming ratio of specific heat gamma as 1.4 and the air standard efficiency, which you need to calculate, coming out to be 58 to 62. The crank radius of a IC single cylinder IC engine is 60 mm, and the diameter of the cylinder is 80 mm. The swept volume of the cylinder in centimeter cube, it is coming out to be 603. A turbocharged four-stroke direct injection diesel engine has a displacement volume of 0.0259 meter cube. The engine has an output of 950 kilowatt at 220 rpm. The mean effective pressure MPa is closest to the, okay, closest to the 2. Okay. So likewise, this kind of numericals will be asked in the gate examination. We will take one or two examples, some more examples, and then we will close down with these today's topics. Let me check. A diesel engine has a compression ratio of 17, and cutoff takes place at 10% of the stroke. Assuming ratio of specific heat R as 1.4, the air standard efficiency in percentage. Okay, this was 2014 gate paper. So answer is 50 to 59 to 16. But how it is being calculated, you can see the detailed solution, PV diagram, 1 to 2, because it is which cycle is given, diesel engine. So 1 to 2, 2 to 3, constant pressure heat addition, 3 to 4, 4 to 1. So the efficiency of the diesel engine is 1 minus 1 by RC to the power of gamma minus 1 in bracket rho to the power of gamma minus 1, rho minus 1, where R is nothing but the compression ratio, and rho is nothing but the cutoff ratio. So compression ratio R is equal to V1 by V2 is equal to 17. Okay. And then V3 minus V2, that is 10 by 100 into V1 minus V2. So we calculate the value of V3 by V2 as 2.6. Therefore, cutoff ratio is coming out to be V3 by V2 is equal to 2.6. Now put the value in this equation. That is 1 minus 1 by, okay, to the power of gamma minus 1 in bracket gamma to the power of rho to the power of gamma minus 1 divided by rho minus 1. So it is coming out to be 59.6%. So you have to solve these questions like this. Thermal efficiency of an ideal diesel cycle. Okay. The increases with the increase in the cutoff ratio, decreases with the increase in the cutoff ratio, or does not depend on cutoff ratio, may increase or decrease with the increase in cutoff ratio. So option 2 is the correct answer, that is decreases with the increase in the cutoff ratio. So here explanation you can see here, the 1 to 2, 2 to 3, 3 to 4 to 1. The processes are given, that is 1 to 2 is reversible adiabatic compression, then 2 to 3 is constant pressure heat addition, 3 to 4 is reversible adiabatic expansion, and 4 to 1 is constant volume heat rejection. So cutoff ratio is the ratio of volume after combustion to the before combustion. That is cutoff ratio rho is equal to V3 divided by V2. So V3 divided by D2. So compression ratio is equal to V1 divided by V2. Compression is happening between the 1 to 2. So V1 divided by V2. The efficiency of diesel cycle is given by 1 minus 1 by gamma rho, RC to the power of gamma minus 1 is equal to rho to the power of gamma minus 1 divided by gamma in bracket rho minus 1. So this is the important point. This is the equation which you have to select, and which will give you that decreases with the increase in the cutoff ratio. The compression ratio of a comp- CI engine is less than 5, 12 to 20, 10 to 15, 5 to 10. So it is 12 to 22, because SI engine petrol is used as a fuel, in diesel engine diesel is used as a fuel. Petrol engine draws a mixture. वीडियो बंद बरं. So here I would like to draw your attention with the explanation, that is a petrol engine is used as a fuel in SI engine. In CI engine, the diesel is used as a fuel. Petrol engine draws a mixture of petrol and air during the suction stroke, whereas in diesel engines draws only air during the suction stroke. Pressure at the end of the compression is about 10 bar. Here in this case, CI engine, the pressure at the end of the compression stroke is around 35 bar, because you know that compression ratios are more, and we have to reach to the pressure where when the atomized fuel is being sprayed in the diesel engine, the combustion should take place. Okay, burning of the gases will be there, burning of the air fuel mixture. Then in case of the petrol engine, the charge, that is petrol and air mixture, is ignited with the help of the spark plug. Whereas in case of the diesel engine, the fuel is injected in the form of a fine spray, and the temperature of the compressed air is about 600 degrees centigrade at a pressure of about 35 bars. In SI engine, it is necessary to use the carburetor to atomize, vaporize, and meter the correct amount of the fuel according to the requirement. And in fuel injection pumps and atomizers are used to inject the metered quantities of the fuel at high pressure according to the requirement. So petrol engine has a compression ratio of approximately 6 to 10, and diesel engine has a compression ratio of approximately 12 to 22. The combustion of fuel takes place approximately at a constant value In other words, it works on the Otto cycle. The combustion of fuel takes place approximately at the constant pressure, or in other words, it works on the diesel engine. Here, the SI engine will have the less vibration, hence smooth running, more vibration, more rough running, and produces more noise compared with the SI engine. In case of the CI engine weight is less. In SI engine weight is more. In case of the CI engine. In SI engines, means petrol engine, it emits the carbon monoxide, whereas the CI engine, it emits the carbon dioxide. So here, the compression ratio of a compression ignition engine is from 12 to 22. Now, which element regulates the pressure stroke in the fuel injection pump of a diesel engine? Which element regulates the pressure stroke? Whether the needle valve, pump shaft, control rack, or lift of the plunger. So answer is control rack, which basically regulates the pressure stroke in the fuel injection pump of a diesel engine. So what is the function of the control rack? Control rack is used to regulate the pressure stroke in the fuel injection pump of a diesel engine. A diesel engine has a compression ratio of 16 and cutoff takes place 6% of the stroke. What will be the cutoff ratio? Okay, cutoff ratio is 1.9. How to calculate it? For example, this diesel engine is being given PV diagram, temperature entropy diagram, compression ratio, gamma is equal to V1 by V2, cutoff ratio, RC is equal to V1, V3 by V2. Calculation, if you do, compression ratio is equal to 16 is equal to V1 by V2. So V3 minus V2 is equal to 0.06 in bracket V1 minus V2, and then calculate it, it is coming out to be putting in this equation 1.9. Okay, so let me take a few more examples, then we will close down with this topic today. Which of the following is not related to the spark ignition engine? That is ignition coil, spark plug, fuel injector, or carburetor. So naturally, ignition coil is used, spark plug is used, carburetor is used in SI engine, but fuel injector is not basically required. So petrol engine, spark ignition engine, you know the differences which you have studied now. Petrol and air mixture is sucked during the suction stroke. Here injector or atomizer, here carburetor is there, here spark plug is there. Compression ratios are very high compared with the petrol engine and all these things. Yes, one of the good question. Cryogenic engine is used in pushing a submarine, in rocket launching, in helicopter, or in aeroplane. Okay. In rocket launching, engine is used in the rocket launching. So we have to study this topic of the cryogenic engine. That is, it is the last stage of space launch vehicles that makes use of the cryogenics. It is the study of cryogenics means it is the study of production and behavior of the material at extremely low temperatures to lift and place the heavier objects in the space. The cryogenic engine makes use of liquid oxygen and the liquid hydrogen as propellants, which liquefy minus 183 degree to the minus 253 degree. Most submarines, except nuclear ones, have a diesel electric engines. Okay. So all these things will be there. So with this, today we have completed the 2 hours of the basically the lecture in the diesel cycle and the dual fuel cycle, and taking up the gate practice examples on the auto cycle, dual cycle, and the dual fuel cycle. So you can see here what the change is there. Most of the time the numericals will be there, which is based on this one, based on this topic. So therefore you must read it fundamentally, try to clear your fundamental, and try to do certain exercise, and try to do the solve the problems. You have to practice the problems, then only you can solve the mcqs. If you don't know the formula, if you don't know the fundamental, you cannot solve this kind of questions. So thank you very much. Shall I end the meeting now? Hello? Yes,
Hello.
Neeraj.
Yeah.
Yeah. So my topics are over. So shall
Okay.
we will end the meeting now? Huh?
Okay, sir. Okay.